Okay, so today we're going to talk about electrophilic aromatic substitution. And this is a really big area within chemistry and organic chemistry, so make sure that you know this. This is big stuff, okay? This is a really important lesson. Now, these reactions are specific to benzenes. You can't use them on double bonds otherwise, because if you think about this is a benzene. If you add Cl2 to it, it's not going to react. It does not react like other double bonds do. So these are specific to benzene. Okay, in general, the mechanism for what we call an EAS, or electrophilic aromatic substitution reaction, is actually a substitution. So what you're doing is you're taking an electrophile and substituting it or exchanging that for a hydrogen through this mechanism. And here's the general mechanism. First of all, you have to have an electrophile. So benzene comes and grabs benzene comes and grabs the electrophile with its electrons, which is the slow step. It's the slow step because you're going from an aromatic uncharged species to a charged species right here, okay, that's not aromatic. We'll talk about how this is stabilized in just a second, but then a base comes along, removes that hydrogen that's originally there, because remember there's hydrogen on each of these carbons here, right? Base will come along, remove that hydrogen, and electrons fall back down, and you restore aromaticity. The reason why this can even exist is because it's resonance stabilized. You can have 3 different resonance structures here to spread that positive charge out, That's how you get this. Okay? I'm going to keep coming back to that as we talk about these other types of reactions. So the first type is going to be an aromatic halogenation. And what we do here is we can either take FeBr3 or AlBr3 with Br2. You could also do this with FeCl3 and Cl2. You just cannot use I2 because that kind of explodes. So what that will do is it will make a Br. If you use Cl, then obviously it makes Cl. So the first thing that we have to do is make the electrophile. Remember? Let's go back up here. See how that's the first thing we have to do is react with electrophile. So first we have to make the electrophile, then it can react with benzene, and then it's sort of standard as to how that happens. So we've got Br2 and FeBr3. This is a Lewis acid, so that means that it basically can accept electrons, right? So the bromine electrons will come and donate over here, and you end up with this weird kind of thing with a positive charge, electrophile, right? Well, this bromine's not very accessible. You can't access it very well. So instead, these electrons come and grab the thing that's on the outside because that's all they can grab. Electrons go back over. Remember how this is resonance stabilized. I drew it out this time. I didn't in other times, but it always still happens that way. And then the FeBr3, this guy will come back and grab him. Electrons fall back down, and you end up with the bromine right there. And so that's sort of the mechanism. Okay, that's your halogenation. Next comes sulfonation. And there's a few variations of how this mechanism is presented. It depends on which way you're going to look, which book you're going to look in, honestly. But they're really doing the same thing, in that you're adding H2SO4 in heat, and that is going to make SO3H. Now, some people, and you'll see this in some text, use SO3 and H3O plus in heat. So they're all sort of making the same type of electrophile. And then notice that this is H2SO4. Make sure you know how to write H2SO4 when you make these electrophiles, okay? Electrons will come and grab that hydrogen, and then they go back to the oxygen. So, sorry I flipped you around a little bit, but this is where the oxygen with 2 hydrogens is. And that's basically a water ready to leave, right? So it leaves, and you end up with a positive charge on that sulfur. If you were instead to start with SO3 and H3O+, that's going to also make this type of electrophile. So once you have the electrophile, it's a very standard type of reaction, right? Because these guys come and grab that sulfur. A base comes to remove the hydrogen, electrons fall back down, and there we go. Now yes, this is always resonance stabilized, that still happens, but I didn't draw it out this way just to sort of make life easier. In a similar vein, nitration occurs, this is sort of like the other side of the coin. If you have HNO3 with your H2SO4, you'll actually get an NO2 group coming off of that benzene. So here we go. We've got nitric acid and sulfuric acid. Now mind you, this is fuming nitric acid and fuming sulfuric acid. And sulfuric acid, its pKa is even lower than that of nitric acid. So this is more acidic than he is, which is why these oxygen electrons will come and grab that hydrogen. You've got to have some rearrangement at that point though, because these electrons will come in and the water leaves, giving you your electrophile. Now it's the same thing as what we've done before. These electrons come and react with our nitronium ion there. A base will come and remove that hydrogen, electrons go back, and we end up with NO2. Now, cool thing, once you have that NO2, then you can reduce it. So you can use Fe or Zn with HCl to do that, or you can just use our standard palladium on carbon to do that. Okay. Next comes Friedel-Crafts alkylation, excuse me. And basically what we're going to do here is we're going to use an alkyl halide, an AlCl3, to put an R group on to that benzene. Now, when I say R group, I mean carbon bonds, carbon chains, right? Of some sort or another. And here's how we form the electrophile. Electrons go from the chlorine to the AlCl3. Gives you this sort of strange intermediate. Forcing, because chlorine does not like to have a positive charge, these electrons leave. And you end up with an electrophile of just R plus and AlCl4. So there's our electrophile. Electrons come from benzene. Notice how this is very standard. Yes, this is probably the base that you're using. If you want to show that that's a base instead, that's fine. So that's going to come and grab that hydrogen, electrons go back, and there's your R group. That sounds great and all, except for the fact that realize you just made a carbocation. Well, when you make a carbocation, it can rearrange. So, you gotta be careful using this reaction, because once I hit this with AlCl3, that's what you're going to try to get, but that's not what's going to actually react with benzene, because you're going to have a shift. So remember, hydrogen can shift over here, and when that happens, the positive charge is here. Wherever the positive charge is where it's actually going to connect to the benzene ring. How do I know this shift will occur? You've got a primary carbocation, and there's a secondary position right next door where that carbocation would be more stable. If it can be next door and be more stable, it will want to go there. That's how I know. Same thing here. Once you make that positive charge right there, positive charge is on a primary carbon, and right next door is the most stable benzylic position. So that's going to fly over there like nobody's business, okay? And when it reacts with this guy, then you're going to end up with this. So these outcomes are not exactly what you may expect looking at the starting materials. So be careful there. Now mind you, if you have something that will make the most stable carbocation, then that's actually probably what you're going to get. So in this case, you've got a carbocation that would be a tertiary. It's no need to rearrange that, and so this is a totally fine reaction to use. Also be very careful of sp2 carbons, because this is not going to undergo a positive charge. Remember how that's just completely unstable. Also, just to let you know, this is a preview, but really hopefully we'll come back to this later. When using something with a nitro group in the benzene, these guys don't work very well. Okay, so what do you do if you don't want a rearrangement? Well, let's look at the other alternative here. We can use a Friedel-Crafts acylation to do something similar to the alkylation. And these are using acyl chlorides with AlCl3, and the difference is you end up with a C double O bond right here. Very similar mechanism. So the chlorine comes and grabs the Lewis acid of aluminum, and then he leaves. The cool thing about this one is that the carbon, the positive charge where that electrophile is stabilized through resonance. Now granted, you're not going to have a huge amount of this, but the point is that he's not going to rearrange, which is pretty cool. Because now we can say, okay, uh-oh, I should have had that go to that carbon right there, shouldn't I? Sorry about that. So these electrons come and grab that carbon, and then AlCl3 come and grab that hydrogen, electrons go down, and you end up with the acyl group on there. Then you can actually reduce that C-double-O bond so that it never even existed. And we can use this with what's called the Clemmensen reduction, or you can just do this with simple palladium on carbon and hydrogen. Okay, I know that was a lot. You may need to replay this video. That's okay. Try to write these mechanisms out on your own and make sure that you know how to do all of them, and you'll start to see, hopefully, that they're very similar. Okay, thank you.